Welcome to The Explainer. We're surrounded by numbers, stats, and studies all day, every day. But what story are they really telling us? Well, today we're going to give you the mental toolkit to see right past the surface and read data like an absolute pro. So let's dive in.
Okay, let's kick things off with a little pop quiz. Picture this, a study in a classroom. Observers see 6 boys and 4 girls engaging in disruptive behavior. Now, just based on that, who's the more disruptive group? I bet an answer jumped into your head almost immediately.
But what if I told you that your first instinct is probably wrong? Yeah, the simple answer here is definitely not the real story. Stick with me for a few minutes, and we're going to break down exactly why and what you need to look for to find the actual truth.
All right, our very first tool is all about one thing: making fair comparisons. And to do that, we need to talk about the power of the humble percentage. So you look at this chart, and it seems pretty obvious, right? 6 is definitely more than 4. So, case closed. The boys are more disruptive. But this visual, this simple count, is hiding a really crucial piece of the puzzle. And here it is, the big reveal. Turns out, the study had 25 boys in it, but only 16 girls. And when we do the math and turn those raw numbers into percentages, the entire story flips on its head. 24% of the boys were disruptive, but 25% of the girls were. Whoa! Suddenly, it's a completely different picture. This is why just comparing raw numbers between groups of different sizes can be so misleading.
So what is a percentage actually doing for us here? Well, it's basically putting everything on a level playing field. It takes a number and shows it as a slice of 100. This way, it doesn't matter if you have 16 girls or 1,600 girls, you can make a true apples-to-apples comparison. It should be the very first thing you look for anytime you see raw numbers being stacked up against each other. Okay, so percentages let us make fair comparisons. Great. But what about understanding the data itself? The next logical question is usually, so what's the typical score? What's the average?
Now, the tool most of us know and love is the mean. And that's really just the technical name for what we all call the average. You know the drill: add up all the scores, divide by how many there are, and bam, you've got your number. It's simple, it's fast, and you see it used absolutely everywhere.
But here's where we need to be careful. Is that average always the best way to describe what's going on? What happens if you have one score that's just way out there? A wild outlier that's much higher or lower than everything else? Does the mean still give you a good picture of what's typical? Check this out. On the left, you've got a nice tight bunch of scores, and the mean is 57.6. Makes sense. Now, look at the right. We threw in 2 extreme scores, a super low 17 and a super high 92. Look what happens. The mean gets dragged down to 56.7. But look at the median. That's just the number in the dead center. It barely budges, staying right at 58. It tells you a much more honest story about where the real center of the data is, because it isn't getting yanked around by those crazy outliers. And this quote just sums it up perfectly. Whenever you've got those wild outliers in a dataset, the median is often a much more accurate, a much more honest reflection of the typical score. Why? Because it's closer to where most of the actual scores are hanging out. But knowing the typical score still isn't the whole story. Not by a long shot. To really get what's going on, you have to look beyond the average and understand how the data is spread out. Let's play out a little scenario. Imagine 2 different classes. They take the exact same test, and, incredibly, both classes end up with the exact same mean score, 75%. So, on paper, you'd think their performance was identical. But was it? Okay, so here's Class A. Take a look. Almost every single student scored right around that 75% average. See how the scores are all bunched up nice and tight? We call that low variation, and it's measured by something called standard deviation, which here is super low, just 0.1. Now here's Class B. Remember, they got the same 75% average, but wow, look at the difference.
The scores are all over the place. You've got some students who absolutely crushed it and some who really struggled. The scores are widely spread out. This is high variation, and you can see it in the much, much higher standard deviation of 2.5. So, that thing we just mentioned, standard deviation, that's our next tool. It's really just a single number that tells you the story of the data spread. It summarizes how far the scores deviate or stray from the average. A low number tells you everything was consistent and clustered. A high number tells you the results were scattered all over the map. It adds a whole new layer of understanding that the average alone just can't give you. Okay, so we have the tools to analyze the numbers, but now we have to take a big step back and ask an even more fundamental question. Can we even trust this research to begin with? It's time for a quality check. And this quality check really boils down to two huge ideas: reliability and validity. Think of it like this. Reliability asks, are my results consistent? If I did this again, would I get the same thing? It's all about dependability. But validity asks an even tougher question. Am I actually measuring the right thing? That's all about accuracy.
The best way to think about it is with a target. If all your shots are clustered together, but they're way off in the corner, your method is reliable, it's very consistent, but it's not valid because you're not hitting the target. If your shots are just scattered everywhere, well, that's neither reliable nor valid. The goal, of course, is that beautiful tight cluster right in the bullseye. That's when you have both.
And this brings us to a really critical point. You can be reliably wrong. Think about that. You can get the same incorrect result over and over again. But you cannot possibly be valid. You can't be getting the right answer if your results are all over the place and inconsistent. So you have to be reliable before you can even hope to be valid.
Whew. Okay, we've analyzed the numbers with percentages and medians, we've checked the spread, we've questioned the quality of the research itself. Now for the final step, putting it all together to draw smart, responsible conclusions. And here are the big rules of the road. First, and this is huge, your conclusions can only be based on the evidence you actually have. Don't leap beyond the data. Second, always be on the lookout for limitations or potential errors. And third, be so careful about generalizing. Just because something was true for a tiny little sample does not automatically mean it's true for an entire population. You always have to ask, was the sample even representative in the first place? Ultimately, making a generalization is a massive decision. It's the moment where you say, okay, what I found in this small group, I think it applies to this much bigger group. And that is a leap you have to make with extreme caution and a lot of good evidence. Because at the end of the day, the data is just the beginning of the conversation. It's never the end. So the next time you see a headline with some big splashy number or a chart that seems totally obvious, just pause, take a breath, use this new toolkit, and ask yourself, what is the story this data is really telling me?